In the last lecture, we discussed distinguishable particles, and for that we derived the configuration. Then the identical particles, and in the identical particles we discussed bosons. For identical particles, which are fermions, we derived the configuration in the earlier lectures. And then in the previous lecture, we just tried to maximize this configuration, and for this we first discussed the general method, and then we discussed the Lagrange multiplier method. And with the help of that, we maximized this configuration, and this came out as the number of particles, and this is the density of states, mean the available states. Alpha and beta were constants, and now we will maximize this configuration and then maximize this configuration. And we will derive the same, the number of particles in terms of the number of available states. So starting from this one, the identical particles, and they are bosons. And this is Q. You remember that we defined a new function, and that function was G, and G was equal to log of Q plus lambda 1, means the first Lagrange multiplier multiplied with the constraint, the first constraint, and then lambda 2 and the second constraint. And this thing goes on if the number of constraints are more. We are having only two constraints, so this is then equal to log of Q, and this was alpha times the first constraint, then beta times the second constraint. So according to this, the constraints we already know that what are the constraints? The number of particles n, they should not exceed, means summation on I from 1 up to infinity, and they are n are for any number n it is running. Similarly, the total energy is equal to summation on I running from 1 up to, let me write here n in order to be consistent with this notation, and this is nn times En. So these are the two constraints. This is F1 and this is F2. So according to this, we are writing our G function here, and G is equal to log of this Q. And Q we are having is phi from I running from 1 up to infinity, and nn plus dn minus 1 whole factorial divide by nn factorial dn minus 1 factorial. This is our log Q, and then plus the first Lagrange multiplier, and the first constraint is n and minus summation on n. So summation on I, and this is nn. This is clear that I is running from 1 up to a number n or up to infinity, and plus beta, and here is E minus summation on I and nn En. So this is our G, and now we will calculate this one. As you know that when log is applied on a product, then it converts it into summation. And when we do summation on these terms, we are actually writing the nth term. So we don't need to write the summation. It is understood this is the nth term. And this thing is then equal to log of this minus log of this. So this equals log, the natural log of nn plus dn minus 1 whole factorial minus log of nn factorial dn minus 1 factorial. And plus is here we don't apply any log here, so we will just write them alpha as it is and plus beta, and this is also as it is. And here we are now using the Stirling's approximation. The Stirling approximation, and the Stirling approximation was, you remember, that it is log of z factorial is equal to z times log of z minus z, provided this z is a very, very big number. And here we know inside here, nn is a big number, dn is a big number, so that's why we can approximate it with a Stirling approximation. And this thing will be equal to nn plus dn minus 1 log of nn plus dn minus 1 minus nn plus dn minus 1. So this is z log z, right, minus z here. So this is the Stirling approximation, and I can convert here, means the approximate symbol here. And what about this one? Now if I look at this one, it's again a product of this. So I will have to use first the product, like minus log of n factorial, and then plus log of this one, and this minus will be multiplied with that, so minus log of dn minus 1 factorial, and plus the same means alpha with its terms and beta with its own terms. So I have just expanded this one. Now if I look here, means what I'm interested in finding the value curly g over curly nn equal to 0. Means I will differentiate this g finally in order to have such a relation, and this is with respect to nn. So wherever I'm having the nn terms, then I will have to calculate for that. If you look here no nn term is involved, so I will just keep it like this. I will not expand this one with the Stirling approximation, but only these terms I will expand. So look here, this thing is then equal to this term, and this is nn plus dn minus 1 log of nn plus dn minus 1 minus nn plus dn minus 1, and then minus. So what about this one? It will be nn log of nn, and then minus, and this minus with this minus will become plus, and nn here. And minus this term will come as it is, plus this term, and plus this term. They will come as it is. So I have just expanded this thing into the nn. Now I can apply the derivative. So by applying means differentiating it with respect to our variable. Our variable, which is in the general form, was xn, and here we are having our variable as nn. So I will just simplify this with the help of this, means just taking the derivative. So curly g over curly nn is equal. Now first of this, you see, this is involving nn, this is involving nn, so they are two two variables, and on two variables when you apply a derivative, you just convert them with the help of product rule. So first function, which is nn plus dn minus 1, this is first function, into derivative of the second, so it will be 1 over this one, and it is nn plus dn minus 1. It is a derivative of this one, plus the second function is this one, into derivative of this one. What's the derivative of this one? Here you will get 1, 0, 0 here. So it will become 1, so you can write log of nn plus dn minus 1 here. And when you come here, then the derivative of this one with respect to this will become minus 1, because dn is 0, 1 is 0, nn becomes 1. And when you come here, then you will have again minus here, and you will apply the product rule. So first function into derivative of the second function plus second function into derivative of the first function is 1. So it is over there, plus nn derivative comes out to be 1. Then minus, we will apply now the derivative on this one, because here we are having this term is going on. And what about this nn terms is 1? What about this term? This term going to 0 because it's constant with respect to nn. So it's 0. About this one, alpha means minus alpha times, okay? Here it is plus alpha, so I will write plus alpha, and then it is 0 and minus 1 here, and I am having minus 1 here plus beta, and this one comes out to be 0 and this one comes as minus en. So this is minus en. Now our result is almost final, and look here, this minus 1 cancelling with this plus 1, and this is cancelling with this, so we got another 1 here. And if I look here, nn is cancelling with this nn, and it is minus 1 when it comes out. So minus 1 here and plus 1 here, so these two terms are also cancelling, and we are having that this thing is equal to this one we have cancelled there, so log of nn plus dn minus 1, and this minus with this minus log of nn, okay, minus log of nn plus, and it becomes minus alpha, and then minus beta en, and this thing is equal to 0 because we will find the extreme values, and extreme values, the first derivative will be equal to 0. The second derivative we have checked in the earlier case that it was coming out to be negative. Even you can check it here as well, and this will tell you that this is the maximum you are on. Like take the derivative of this one and this one, you will finally get a negative value. So this one is then equal to log of nn, this log of nn plus dn minus 1, and you can combine these two, and this comes out to be log of nn plus dn minus 1 divided by nn here. So this is the log of it is equal. If I move it the other side, then it is alpha plus beta en. And now this is a natural log, so if I take exponential on both sides, then let me write taking exponential on both sides, what we will get? We will get this exponential and natural log will cancel each other, and nn plus dn minus 1 over nn is equal to e to the power alpha plus beta en. This is the expression that we got, and now I can write this one. Nn, if I multiply here, then nn plus dn minus 1 is equal to nn e to the power alpha plus beta en. And now what is required? The required is we want to have the terms in terms of nn. So I want to have this one. So how I can write this thing? I can write this is dn minus 1 is equal, if I take nn is common, then it will be e to the power alpha plus beta en minus 1. Because when this nn comes on this side, it becomes minus 1, and nn is common here. Now nn will be equal, nn is equal to dn minus 1 divided by e to the power alpha plus beta en minus 1. And this is the distribution. This is the distribution of particles, mean the number of particles in terms of the energy states or the density of states for a maximized Q, for identical bosons. So we are having this is one maximized relation. This one is another maximized relation. And now we will move to the case of identical fermions. And for identical fermions, we will go on through the same practice. So let's consider the identical fermions. And the case of identical fermions means identical particles, and those particles are fermions. So here I will just go on with the Q here, and we will skip some steps because it is not that difficult, just the application of the log and then taking the exponential and then rearranging the terms, and we will get the relation. And we will first write our G, and G is equal to log of this thing. So when you take log of this, then it will be log of dn minus log of this. So the log Q will be log of dn factorial minus log of nn factorial and dn minus nn whole factorial. So this is the first step, and then plus alpha times the constraint and beta times the constraint. Means just like this one, you will write alpha times the constraint, beta times the constraint. We will utilize those values in the derivative, so I'm writing it as it is. Now look here, I don't need to expand this one because it is with respect to nn, it is constant, so automatically it will go to 0, so no need to expand this one. Just expand this term, and G is then equal to this term plus minus here, they are in product. And when you will apply the product, so log of nn factorial and plus this, so it is minus here, so minus, and log of dn minus nn factorial.